Welcome students. Let us study the strength concept and load balancing concept for pre-stressed concrete. The concept of stress is already been covered in the previous lecture. So we will directly start from the strength concept and load balancing concept. First, let us understand what is strength concept. So it is basically pre-stressing for combination of high strength steel and concrete. So if a reinforced concrete, as we all know, that steel takes tension and concrete takes compression. The couple that is formed by the resultant of compressive force C and the tensile force T resists the external moment. This is in conventional concrete. Same thing happens in pre-stressed concrete. The same concept can be applied for pre-stressed concrete sections also. Now the pre-stressed concrete is considered as a combination of steel and concrete. Okay, we do provide steel and concrete in pre-stressed concrete, while steel takes tension T and concrete takes compression C. Now T passing through the tendon that is provided and the compression C is passing through the CG of stress distribution, so that the two materials form a resisting couple. So here also both the materials will form a resisting couple to resist the external movement. Now this concept has been well utilized to determine the ultimate strength of pre-stressed concrete beams. So it is very simple. So this is the normal stress diagram which we draw, wherein we show this is C and here there is tension T. So this both will form a couple and the stress diagram will change to this stress diagram where this is C and this is T. So both the stresses together will resist the external movement. So it is basically the strength of steel and strength of concrete, the simple concept of strength. Now let us see what is load balancing concept. Here in this particular concept, it is pre-stressing that is achieved by load balancing. Now what do you understand by load balancing? The load that is coming onto the structure is well balanced by the tendon that is provided within the structure. This concept is developed by a person called Lin. And the working is all the flexural members is transformed into a member under direct stress. So there won't be any flexural stress that will be experienced by the structure, but there will be only direct stresses. So if this is a beam, this is the CG of the beam, the tendon is parabolic, okay, where maximum sagging is considered as H. Now why do we provide the tendon as parabolic? The reason behind this is there are two ways we can provide the tendons. We have already considered it in the previous concept of stress. One at the CG and one at eccentricity E from the CG, that is this. Now what happens is, we know if the beam is simply supported, and there is a UDL on top, this is the bending moment diagram or the deflection diagram you can say, where sagging occurs maximum at the midspan and it is zero at the ends. We know that the deflection is going to be like this for this particular beam. That is the reason we provide the tendon in such a way that maximum sagging happens in the midspan. So the tendon is provided in a parabolic manner with the maximum vertical distance at the center is as H and it is 0 at the ends. Okay, so this point is A, this point is B, and the tendon is provided here with H. So this is a parabolic tendon. Okay, so now if you convert this beam into a free body diagram, that is, instead of a tendon, we consider it as a free body diagram for the beam, and the load is shown here. So this will be the load, and this will be the tensile force or the tensile load. So if you consider this midspan as point C, this as A, and this as B. So what is seen, I will just draw the tendon again. This is point C where this is H, and if you draw this at any point, this particular distance is distance Y, and distance from the center to this point is taken as X. Okay, now I will just draw the diagram from the center till the end, that is whatever I am showing in the dotted box. Only this part I will slightly elaborate and I will draw it again. So it starts from point C. Okay, so this is the point C. This is point C, that is the midspan. So I randomly choose 2 points here. One is P and other one is Q, where here the tension is acting like this. So two components, the vertical and the horizontal component, if this is theta 1, this is theta 1, then the horizontal component will be T cos theta 1 and T sin theta 1. Similarly, if this is the tensile force, the two components, the horizontal and the vertical components, will be T sin theta 2, T cos theta 2, where this is theta 2. Now, distance from this center till point P, let us consider it as x1, and distance from center to point Q is considered as x2. Okay, so what we have done, we have considered a concrete as a free body, and a tendon is replaced by forces acting on the concrete, that is this particular figure. Then this figure shows you a parabolic profile of the tendon with maximum sagging at that is H at the center with respect to CG of the section. Here we have considered 2 points, that is P and Q, at a distance of x1 and x2 from the center, that is from the midspan, and the cable is under uniform tensile force T. So there is a uniform tensile force T that is marked here. So we have written both the components, that is horizontal and vertical components, for this tensile force with respect to horizontal. So from the figure, from this particular figure, if you refer to this figure, we will be able to write the equation for the upward force. So upward force is nothing but T sin theta 2 minus T sin theta 1. So this is theta 2, so I have taken this as positive. This is going downward, so it has to be negative. That is the reason it is basically summation of all the vertical forces. So upward force will be nothing but this T sin theta 2 minus T sin theta 1, which is T sin theta 2 minus sin theta 1. Now if this H is less than L, which is actually the case in every time, H, that is the maximum sagging here, will be less than the total length of the beam, obviously. What happens is this theta 1 and theta 2 are very small. So in this case, this sin theta 1 and theta 2 will not give us any answer, or there won't be any value. So this sin theta will be approximate to tan theta. So we will substitute, instead of sin theta, we will take it as tan theta. So the equation for the upward force, therefore upward force will be equal to T tan theta 2 minus tan theta 1. Now, we have already learnt in 8th standard the equation for parabola. Equation of circle, equation of arc in xy plane. So, there is an equation for parabola. We are going to use this equation as we have a parabolic profile for the tendon that is provided. So, this equation is nothing but y is equal to 4 into h L square, the total length is x square minus L square by 4. You need not derive this, you can directly write, and I will mark this as equation 1. So this is equation of parabola that we are going to use. Now the first derivative of this particular equation with respect to x will be equal to 4h into L square. This x square becomes 2 into x. This constant becomes 0. So this is 2x. So the first derivative of the equation of parabola is given by dy by dx equal to 8hx upon L square. Okay, so this is the common derivative. So now if we take it with respect to x1 and x2, it will be dy by dx1, which is equal to 8hx1 upon L square. And if we take it as dy by dx2, it will be 8hx2 upon L square. Therefore, the upward force can be written as T into that, instead of tan theta, we will substitute it. This will be equal to tan of theta 1 and this will be equal to tan of theta 2 from the figure. It forms a triangle. That's the reason we had taken that sign as tan. So this is theta 1, tan is opposite upon adjacent of this is theta, this is the opposite upon adjacent. So it becomes h into x divided by L square. Okay, so taking that, we can write this as tan theta 1 and this we can write it as tan of theta 2. So this upward force finally can be written as T into 8 of h upon L square into x2 minus x1. I have just taken this 8h upon L square as common. So this can be written as this. Now if we take this x2 minus x1 equal to 1, that is unity, then the upward force per unit length will be equal to T into 8h upon L square. So from equation 1, that is the second derivative. If you take the second derivative of equation of parabola, d square y by dx square, it is nothing but 8h upon L square. Hence, we can write P equal to T of d square y by dx square. So, depending on the shape of the tendon, the load can be balanced in the section. So now we have taken a parabolic profile. So we have taken equation of parabola and we have calculated the first derivative and the second derivative. And also considering the diagram and the resultant of tensile force and the two components, we got it is equal to 8h upon L square, which is same as the second derivative of equation of parabola. So by considering the different shapes of the tendon, the load can be balanced. This is what is proved in this particular concept. Okay, so load balancing concept is basically you balance the external load with the help of different shape or profile of the tendon that is provided in pre-stress. Thank you.